Hi and welcome to Unit 3, Topic 2, Video 3. In this video we're going to talk about polar form in 3 dimensions. So, 3 dimensions means we have 3 unknowns. We have x, y and z in component form. It means when we get to polar form, we also need to consider 3 unknowns. 2 is not enough anymore. So we have r and we have theta. Theta is the azimuth. And then we also have this altitude, which is called phi typically. Another Greek letter. So, let's have a look at a diagram. So this diagram is a 3-dimensional diagram again. But this time I've got not just the blue component. So imagine you're looking down through that Z point on top onto a page that would look like your standard XY axis. And the blue angle, theta, would be your standard angle from the positive X axis around. It's just we've created this Z. So now all we need to do is, if we have the X and Y axes of a sheet of paper and we've measured the displacement, R, and we've measured the angle around, we just need to know what the angle is to the piece of paper plane. That is the Z angle, and that's phi. It measures how far this vector is sticking up out of the page or sticking down into the page. And we can calculate all those things just by being thoughtful about how we apply our trigonometry. So in this case, R is just the magnitude, which is x squared plus y squared plus z squared, square root. Theta, well, that's pretty easy. It's just tan inverse of y over x. But again, we have to be quadrant aware. So just know your x and y values and where that's leading to help us be quadrant aware with theta. And then phi, we get tan of phi. So phi is this angle. And that's equal to z, the opposite, over the magnitude of this inside, which is the square root of x and the square root of y. So this is actually not quite right there. This should be the square root of x squared plus y squared. But you might be saying, well, you know what, and I actually agree with this, and I'm not sure why I've written this, but let's change this up a little bit, because actually we already know the value of r. We're calculating it up here. So why don't we just say, instead, phi is equal to z over r, and in this case, z over r is going to be an opposite over hypotenuse, so it's sine of phi, and I think that's actually what it is, and I've just put tan down for some reason. So sine of phi equals z over r, and we can calculate our phi, our theta, and our value for the magnitude. Now with the theta we have to be quadrant aware, because it could be anywhere from 0 to 360, but with phi it's either out of the page, which would be a positive, so sine of phi is positive because r is definitely positive, it's a magnitude, and z is positive because it's on the positive z axis. If it's on a negative z axis, it means it's below the page, and we get a fourth quadrant answer, which works because z will be negative and sine of the fourth quadrant angle is negative. So we're happy here. So we don't have to be so quadrant aware there. Let's have a look at an example. Example 3. We're going to write w equals 7i minus 2j minus 3k in polar form and do this calculation. So let's do it now. Let's start with our r. R is equal to the square root of 7 squared minus, also plus negative 2 squared plus negative 3 squared. And that's 49 plus 4 is 53 plus 9 is 62. The square root is 62, and I can't do much better than that, so I'm going to leave it as that. And then we have tan of theta, or theta, is equal to tan inverse, and it's tan inverse of y over x, was our calculation earlier. And so that's equal to tan inverse of negative 2 over 7. Now in terms of being quadrant aware, if we're talking y is negative 2 and x is 7, 7, negative 2, so we're in quadrant 4. In tan we're expecting to be negative, which it is. So let's just make sure we get our angle in quadrant 4. Shift tan of negative 2 over 7, close brackets, and that gives us negative 15.9454, etc. And so we're happy with that. And but that's in degrees, of course. I could do it in radians, and I probably should have, but I haven't changed my calculator settings. But actually I can just quickly show you in radians that's negative 0.28 approximately. And then we can also get our phi value, which is sine inverse of z over r, which in this case, sine inverse of z over r is sine inverse of negative 3 over the square root of 62. So again, we're in that fourth quadrant. We're below. And so sine inverse of negative 3 over root 62. Shift sine of negative 3 over the square root of 62. And that's equal to negative 22.3957 degrees. Or it's equal to negative 0.39 radians. And so this comes out as W is equal to, bracket, the square root of 62, comma, negative 0.28, comma, negative 0.39. And that's enough information there to define that vector perfectly, except of course we've done a bit of rounding. Now we can also reverse this process. So here's a little side note about reversing it. From the diagram shown, we can calculate that Z is equal to R sine phi, and that Y is equal to R sine theta cos phi, and that X is equal to R cos theta sine phi. So I've got my little diagrams there, purple and blue, hopefully that helps. And in the purple and blue, the Z's pretty easy. Z is equal to R, so sine phi equals Z over R, multiply the R through, blah, blah, blah. But we can also get this value here, R cos theta, which is actually irrelevant to our question, but we can transfer that in as a length of the blue one, which means now X, well this is, we get this relationship, cos of theta is equal to adjacent X over R cos of phi. And we rearrange that to get that value. And we do the same thing with Y to get this guy. So I won't go into too much work proving that, but no, it's true, and I'm pretty sure that you could work out Y yourselves. So lastly, in example 4, let's talk about finding these components. So V is equal to, in polar form, 24560. So diagrammatically, this looks like this. 24560. It's got a magnitude of 2. Its direction is 45, which in the light blue sense is down right in between that positive x-axis and the positive y-axis there. But this is on flat at the moment, it's horizontal. And then it rises up 60. So the actual vector itself has got a length of 2 and it's up 60 there. So if I drop this down here, that's a right angle. This is 60 degrees. And this is, in light blue, 45 degrees, and it's got a length of 2. So you can see that this is defining one specific vector. And we can work it out what it is in component form by just doing this. So we'll start with X. Let's go in a natural order. X is equal to R cos theta cos phi, which is equal to 2 cos 45 cos 60, which is equal to 2 times 1 on root 2 times times by 1 on 2. And so that's equal to root 2 on 2. I've just rationalised it there. That's X. And we have, I'm just going to create a bit more space for myself here. Y is equal to R cos theta, no, that's wrong, sorry, R sine theta cos phi, which is equal to 2 sine 45 cos 60. And we get the same thing here because sine 45 and cos 45 are the same, so we get root 2 on 2 here. And then finally, Z is equal to R sine of phi, which is equal to 2 times root 3 on 2. That's just equal to root 3. So in component form, V is equal to root 2 on 2, comma, root 2 on 2, comma, root 3. And that was fun, wasn't it? So that's example 4, and we're through our representing three-dimensional vectors in polar form. All the best.